Okay. So what is the Fourier transform? Is a taking a signal fx, a real space signal, and resolving it various components, and components are along Fourier basis. So what is the amplitude for a wavelength lambda, 2 lambda, 3 lambda, 4 lambda? So you see in music, no? So we have one wavelength, then another wavelength, which is half of its wavelength. So I want to see the amplitude of these waves. That's it. That's a Fourier transform. Okay. And this is amplitude of this sine or cosine. In fact, it's not sine, cosine, it's a combination of sine and cosine. Okay. It's the amplitude of this wave. Okay. And you see, I mean, this is useful when I have a signal like electromagnetic wave coming from the sun. I want to see what are the, I mean, what wavelengths are coming from the sun. And then, of course, many wavelengths are coming, but what is the amplitude of yellow light, red light, green light, you know? So this f hat n is the amplitude. Okay, it happens to be complex because my basis function is complex. And why do I use this one? Because derivative of exponential is exponential. Okay, derivative sine it becomes cosine, and that complicates a bit. Though it can be done, you can work out sine transforms, cosine transforms, but exponential is very convenient because the derivative in exponential is exponential. Okay, now, so that's the whole idea. Okay, and it turns out I'm going to show you how to use this for solving the differential equations. That's what we'll do in the course. It's also used for image processing. Why image processing, or why in music? So image has, I mean, if you take a high resolution image of, let's say, sky, you know, then lots of pixels. And you see, I mean, if I want to save all of it is so much of data, and I don't understand it. But imagine that it has some kind of bright, dark, bright, you know, that kind of a pattern. Then I know it is I can decompose it in some kind of sin x cos y or cos x sin y type. Why? Because here it's like a drum. It's a square drum where bright is going up. Okay, these two bright are up, and dark is going down. So it is like a hump like that. Okay, so we can use these kind of basis functions, and I need only few components of the basis functions. Maybe some component for 2x and sin 2y, and that is very useful to save some numbers rather than saving billion points. Okay, same thing in music. I mean, I don't want to save all possible frequencies. I want to save only the ones I hear. Okay, and it turns out that we can compress it by some clever schemes. Okay, that part we don't do in this course, but that's the whole idea for compression. But for saving images, saving music, or any other signal. Okay, anyway, so that is the whole idea, and I showed you how to do it in a discrete transform. So in computer, I can't really do the integral. Okay, so I will save it, I will discretize it in a discrete number of points in 1D. So this is a the discrete transform. Okay, now this formula, I recommend that if you're doing the project, you should definitely derive it. If you're not, then you should kind of know what this formula is. Okay, I is square root of -1, this I. And j is the integer and n is the integer. And small n goes from -n/2 plus 1 to n/2, and small j goes from 0 to n-1. This is a real space index here, and I showed you what is the Fourier space index. Fourier space indices are this. Okay, if you've done Fourier series, this is revision. If you've not done it, you just treat that as a definition. Okay, but in computer it is saved from 0 to n minus 1 with some translation which I discussed in the last class. This translation. Yes, any question? Okay, now so this is for 1D, 2D and so on, but let's look at 3D. So 3D, I had one picture. Yeah, so 3D Fourier transform involves, so our data is in 3 dimensions. So this is let's say, so we have, this is x-axis, y-axis and z-axis. So I need to do 3 sums, no? So to compute the Fourier transform, so I'll have 3 indices in Fourier space, nx, ny, and z, and I need to do sum along x direction. So let's see. So nz direction first. This is my real space data. Then I multiply it by this exponential and sum along z direction. So I sum along this direction. So how many sums I need to do for every x and y? So here J1, Jx and Jy are fixed, and I'm varying Jz. No, so for this thing, I will just do like, well, actually I made a mistake. This is z. Okay, so this is x and this is y. So please apology. This x and this y and this z. So I first do along z. So all these columns I sum, vertical towers. Okay, so you can just imagine there's a plane, and for every xy we have a column, towers. You sum along that. So after I'm done with this, I get f hat jx, jy, and nz. Our jz is gone, no, because this is only function of nz. So this nz is done. Now I do the next sum. This sum. Okay, so now I will sum over ny. Okay, so this is jy and ny are here, jy and ny. So when I do the sum, then I get f hat jx, ny, nz. Okay, so by the time I come to this loop, I got this. Now I have single direction to integrate, and then I sum over for every nx and y. Okay, now I'm basically going from one component of real, well, 3 component real space to 2 component real, 1 Fourier, then 2 component Fourier, 1 real, then finally everything is real. Fourier, everything is Fourier, nx, ny, and z. Okay, so it was 3 sum. And each sum, you can see that is basically n cube. Okay, so how many nx, ny, and z is n cube? So it's n to the power 6 operations, and it is huge, n power 6. So if n is 1000, that makes it 10 power 10 cube power 6 is 10 power 18. Okay, that's impossible. Okay, that's where we want to use some clever scheme using fast Fourier transform. Okay, so that's what I will describe now, how to do 3D integrals using FFTs. So, but I will show you how it works. Okay, parallel fast Fourier transform. Okay, so complexity, I just want to, well, I mean, I think, okay, I'll not discuss it. I discussed already for weather forecast, the number of grid points are huge. In fact, 1000 is less than what is required in weather forecast. Okay, so you really need a large number of grid points. So we need to use fast Fourier transform and parallel. Okay. Anyway, right now 3D, if you don't do parallel, how is it done? 3D FFT. So what is done in 3D FFT? Sequential. Okay, just sequential. So this was Z direction, and this was X, and Y direction was inside. So what is done right now is along, so we have 1D transforms, no? So basically, when I did this, f jx, jy, jz, exponential, there was jz, nz. So when I'm doing this 1D columns, I'm doing a Fourier transform. So I can do, instead of doing order n, I can do in order n squared, I can do in order n log n. Okay, so we basically use 1D columns, Fourier, well, basically we use FFT on 1D transforms. So each 1D transforms are fast Fourier transforms. Okay, and of course I need to sum over ny and nz, jx and jy here. So we basically use 1D transform which is already written. So there are quite a few of them, but the most famous is FFTW. Okay, this is fastest Fourier transform in the West, MIT. Okay, so this is available for 1D, 2D, 3D. Okay, you can also use it for 3D, but when I use parallel for something which I'm going to describe today, we can use this 1D FFT of FFTW. Okay, I'm going to show you why we need to improve this. FFTW of MIT is not sufficient. In fact, we need to do more work than MIT FFTW. Okay, so let's get there. So if you want sequential, MIT FFTW is good. Okay, if you want parallel with some decomposition, this is good. But if you want, you have a lot of data, then MIT FFTW doesn't work. Okay, I hope that is, I'm going to make it clear. Let me just come to that. So this FFTW, I told you about this quite, I mean, I think it's 20 years old. Probably, yeah, more than 20 years old. Intel FFT has, Intel itself has FFT, which gives similar performance as FFTW. On GPUs, we have cuFFT, CUDA FFT. This is P3D FFT. It is a bit different than these two. Okay, of course, CUDA is a very different ball game. Okay, but then we have our own FFT Kanpur, and this PFFT in UK, and there is hybrid FFT. Okay, it is developed by well, there are several people. Minini, Argentina. Okay, he is the lead developer. Now, so let's look at how we do parallel FFT. Okay, please remember that if you want 3D FFT on a single core, we can use FFTW and it will work. But if you want to do this with more processors, let's say I want to work with 4 processors. Okay, it is a bit cut in this image, but you can see that. I mean, I showed you this in the previous slide. Okay, so there are 3 sums. So I want to divide among 4 processors. Okay, for example, so I had this data. This is Z, this was Y, and this is X. Okay, so we can divide among 4 processors. So this is the there are slabs. You know, these are like slabs. You understand? No, slab is I have the cube. I cut in 4 pieces, and each of them are called slab, and there are 4 slabs. So processor 0, processor 1, processor 2, processor 3. So what do? I can do the 2 sums. Okay, or FFT along Z direction and Y direction I can perform. So Z direction and Y direction I can perform. In fact, we can also do planar FFT. So this is a plane. I can just perform plane FFT, which is basically doing along Z and Y using one function. But it involves 2 1D transforms. Okay, and that is done by single 1D along 1D FFTs. Of course, this will involve first time when I do it, I will be doing along Z column. How many of them? There are 8 of these in, so 8 times 2, 16 columns. Okay, 16 columns. I do this one first. Then once I'm done, then what do I do? Along y direction. So now I will have horizontal columns. Okay, I mean, I hope you get it. So this will be the sum direction. This will be some direction like that. So that is y sum. And I do it for simultaneously. Okay, simultaneously among each processor. So when this sum is being happening along z direction in processor 0, processor 1 is also doing that sum, or processor 2 is also doing that sum. So this is done in parallel. Y direction sum also being done in parallel. The data is available within the processor, so they can do it. But now I need to do at the last step sum along x direction, or FFT along x direction. Then what do I do? I'm stuck. I can't do it because I need to sum along that direction, and each processor has only 1/4 of the data for each line along x. Then what to do? I need to transfer data. Okay, and it involves huge amount of data transfer. Now you can see that what is happening here in data transfer visually. Okay, now so you have to just see it carefully. So processor 0 keeps this part of the data. Processor 0, okay, keeps with itself. This data will keep. It will get from processor 1. So, well, processor 0 will keep this, but I want along that direction. So processor 0 will say, well, I'm going to do this direction, okay? So I will ask this data from processor 1, this data from processor 2, this data from processor 3. Okay, so these data are being transferred from 1, 2, 3 to processor 0. So processor 0 finally will have data like that. Okay, this is the data of processor 0. So I say processor 0. Okay, is that clear? So it's getting, it has one quarter data and 3/4 data it gets from other processors. Okay. Now, what does processor 2 does? What does processor 2 do? Processor 2 will keep this data, diagonal data, this data, processor 2. Well, processor 1, sorry, processor 1. Processor 1 will keep this data, and it will take data, this data from processor 0, this data from processor 1, and this data, processor 2, and this data from processor 3. Okay. So processor 2 keeps again 1/4 of its data, which is along the diagonal. Okay, along the diagonal keeps the data. This one was with itself, but then remaining 3 came from other processors. Okay, and the processor 1 has now this data. Same thing with processor 2 and processor 3. So the data is basically reshuffled. Now you can see that each guy is getting data from 3 other processors and also sending to 3 other processors. Okay. Right? I mean, it's obvious from here. I mean, the data was in fact like that. Now it has become like that. So the overall, we got this data. This is called all-to-all transformation. All-to-all. So I'm going to show you this a bit later. So how to do all-to-all? In fact, there's one function call for this transfer. So in MPI, we do all this data transfer all-to-all. Okay. So that is why it is very expensive. This is communication intensive job. And we discussed that there's a lot of overheads when we send data across the switch. This will go, well, if you are within a node, it will go from one processor to other processor. But if you're across nodes, then it has to go a switch. Okay, and that makes it quite demanding. Now, I would also tell you that normally we use huge number of processors. we may be using something like 10,000 processors. Now, 10,000 processors, that means we are doing how many operations? One is sending to 9,999 processors. So there's a huge traffic at the switch. And that's why this is one of the most demanding parallel algorithms. Okay. Now, so FFTW does this. This was done in 1999. Frigo and Johnson. And it's written in C language, and it's quite fast. And it has some tricks, okay? It tries to optimize for a given hardware. And Intel FFT, okay, this is GPU, so I should not write that. The design is similar. In fact, all of FFTs are designed in similar way, in following FFTW. The notation of data decomposition is FFTW decomposition. It has become standard. Python FFT is FFTW. Okay. Now, what is the limitation? So suppose I have n cube grid. So let's say 1000 cube grid. Then how many processors can I use? So if 1000 cube, then number of planes I can have is how many planes I can get? 1000 planes. So how many processors can I get? Because this is a slab, no? So what is the maximum number of slab possible for n cube grid? N. So a number of processors maximum I can use is n. Now supercomputers now they tell you that if I'm working with 1000 cube, do not use 1000. Use let's say 8000 processors. Because I can do it faster. With 8000, I can do faster than 1000. In fact, slab with 1000 will be not very good. Okay, if I'm doing slab decomposition with 1000 cube, I should use something like 256 processors, because there must be at least 4 slabs. No, if you have 1 slab each, it's not efficient. There will be data communications. So if you want to use processors more than n, then I should use something different. And that's where this new decomposition called pencil decomposition comes into play. And this decomposition is not available with FFTW. Okay, but this is available with P3D FFT and FFTK. Okay, so these are called pencil decomposition. So instead of dividing in slabs, we have towers. Okay, these are called pencils. Okay, so we have, okay, these are called pencils. Now we have 12 pencils in this. Each pencil has more column. I mean, so this one has something like, I can't, let's see, you can see that there are 3 times 4. Each of them have 12 vertical columns. Okay. So, so how do I do it with this pencil decomposition? So here, so please remember that these are the processors. No? So we have NX processors and NX and NY. So the number of processors used are 3 times 4, 12 processors. Okay, so you can quite see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 processors. This is a top view. Okay, in engineering, this is called top view. If I see from the top, I will be seeing these processors and they're colored differently. How do I do it? Now, each processor has data along Z direction, all the data along Z direction. Okay, so it can happily do the sum along Z direction. So FFT along Z direction is doable, and that's what it will do. All of them will do the sum along Z direction, and all of them have 12 columns to work with. Okay, right now in this example. So 12, great, I can do it. Now, after I have done this Z direction, then I would like to do the Y direction. But when I want to do along Y direction, the data is not available, right? So the data, for example, if I go along that direction, is divided along 3 processors. See, I mean 1, 2, 3, Y direction. So now we do the communication like before, all to all, but within groups of processors. So these three guys will talk among themselves. And then data becomes like that. Data becomes, here, well, basically, so here they were vertical talk columns, no? Now after communication, it becomes horizontal columns, horizontal columns, right? Horizontal pencils. So these three communicated, and instead of three vertical pencils, it has become three horizontal pencils. Same thing is done by the second rows of processors, these processors, and they will make these three horizontal pencils. So all of them will make horizontal pencils. Now, how many horizontal pencils are there now? Again, there should be 12, right? So now the data will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It should be the same. Okay. We just that we are labeling differently now. So we have, this is X direction. So we have data available along Y direction, all the data. So now I do the sum along Y direction. Okay. Great. I'm done with Y. After that, what I want to do, sum along X direction, in that direction. Now I need to do again this communications. So so these guys, okay, these guys will talk among themselves, and they make, you can see that there are 4 of these. So instead of 4 columns going along Y directions, or 4 pencils going along Y direction, now we have 4 pencils going along X direction. You can see that the 4 pencils along X direction. Okay, now I can do the sum along X direction. And once I'm done, I have the Fourier transforms, all of it. And in fact, what is available is Nx, Ny, Nz. Okay, remember the Nx, Ny, Nz are the Fourier coefficient, Fourier wave numbers. Okay, Fourier indices, if you like. But the data is Nx, it's consecutive along Nx, but for Ny, I had to hop. Okay, it's available with different processes. Now, so this is called pencil decomposition. Now, how many pencils can I have in principle? So suppose I have n cube data, then maximum number of pencils I can construct is n squared. So n squared is, of course, 2 thinner pencil. Every guy has one pencil each, right? 1 column each. But if I have 1000 cube data, then in principle I can use million processors. Okay, it's not a good thing to do it, but in principle I can do it. Okay.
Sir, wouldn't this method still be bottlenecked by the intermediate state where the processors communicate with each other to change their orientation? Because at that stage, the communication between the processors for their memory, that will still be a linear process.
So yes, I mean, we are doing 2 sets of communications, right? From here to here and here to here. By the way, communication from here to there and there to there is of the same complexity.
Yes, sir, but compared to the actual, so this will only be beneficial when the communication time is far less than the computational time.
Okay. So indeed, there is, I mean, look, if you have more processors and more communication, I agree with that. Okay. But if your code scales well, then I can finish my task in less time. Yes. So look, what I'm saying is I don't want to use only 1000 processors. In modern supercomputers, using 1000 processor is not allowed. In fact, they would say minimum 4000 processors. Okay, because number of processors are huge. So that pencil is required. Now, if I'm doing something like 512 cube, then 1000 is okay. The number of processors 1000 is fine. But if I'm using large number of processors, I mean I have 10,000 processors, then I simply cannot use SLAB. That's one. Now, indeed, with 1,000 processors, if I had 4,000 slab decomposition, okay. So if I have 4,000 cube, now if 1,000 processors, then each of them will have four of these slabs, right? Is that correct? 1,000
Yes.
cube, 4. Now, the total, I mean, efficiency wise, this is better slab, but it will take much longer time than 4,000 cube. I do it with something like 16,000 processors. I need to wait less. Okay. And efficiency wise, it's not that the slab is much better. I mean, the communication here is expensive as well, but it's better.
Yes, sir.
Okay. And
so, but in general, we can't know until we run the program, right?
No, we can. That's why we do the scaling. We do scaling once, and then we can. It is to be reported. I'm going to show you what the numbers we get. The next time we can plan out things. We don't need to run every time and figure out is a bad thing or not. So you do scaling once, and then we'll know that all. I mean, from that we can get a number. I mean, we can estimate time.
Yes.
Now, one more important point. In the pencil decomposition, the traffic is less. Huh? If you see the traffic wise, when these guys are talking, okay, they do not interfere with the second set of processors. So you see, when these processors are talking, they do not interfere with this communication. So you can think of there's a traffic, local traffic, when I'm doing it, which is very useful. So if you arrange your, I mean, that's difficult. In fact, sometimes, most of the time, it's not allowed to the user where you allocate your processor. But if you imagine that these nodes, these processors are within a node, these are within a node, then or within a rack, then this communication will fast, this communication will fast. Okay. So traffic here is not too bad, no? Because traffic is within a block of processors. So pencil is a good decomposition. I mean, it is important to run with more processors. Also, there is a communication among setup processors.
Yes, sir. This is like the idea that they can communicate because they are physically closer is a good thing.
Yeah, if it could be done. I mean, normally they don't allow you. I mean, the supercomputing software, the queue manager will allocate depending on availability of the processors. But if it could be done, then it's great. Some intelligent queuing managers may do it, but in fact, we tried to do it. There's some gain, but we got something like 16% gain. Anando Chatterjee and KAUST scientist, Samad. So they basically did this work. So if you assign it appropriately, or we can get some improvement, but it's not great improvement. Okay, anyway, the bottom line is that if you're more processors, then you should use pencil. And all these are available with MPI. We can do this arrangements. Now, P3D FFT was the first pencil decomposition. San Diego supercomputing lab, again in 1999. Communication. So P is the number of processors, and communication time. Well, it's not, so it is a plus P to the power 2, P to the power 2/3. So communication time increases. That is their result. I mean, there's no proof per se, but there's some hand-waving argument that if you're more processors communicating, then it comes. There's some argument. Okay, I mean, I will not get into that. It can be by section bandwidth. One can argue is exponent to width. Now, they used 64,000, well, 65,536. Now, in computer languages, we call it 64K. So this 64 times 1024. Huh? If you do that, you'll get this number. So everything is 2 to the power n, most of the time. Sometimes we have 3 to the power n. FFT, though we have FFT for any number of data points, but it's most optimum for 2 to the power n. Why? Because branching in a tree is optimum for 2 to the power n. So this was for 8,000 cube. It's published in 2012. Now, there's another one, PFFT. This is a PPIG group, and they use, in fact, even large, 2 lakh processors, 2,62,000 processors. Now, I will discuss a little bit about FFTK, FFT Kanpur. So it's stencil based, and it's done by our group. And we scaled up to 196,608. It's 3 times 64K. 64 times 1024. Okay, so that will give you that. So Sahin 2 is in KAUST, and the best ranking it got was I think 7th in top 500. Now it has come down to around 100. So we went up to 3,000 cube. Well, it has been tested to 6144 cube rate. So, but scaling is up to this. And we use this FFT to do flow solver, which I will describe after my presentation of FFTK. So let's see the scaling. I did discuss it in my previous lecture, but I will redo it now. So we report computation time, communication time separately, and the total time. Okay. Now, it turns out we can plot in log-log scale. If you plot in log-log scale, then we get a linear profile. And so the T computation goes like that. So gamma 1 we expect close to 1, no? Because if you put in more processors, then computation should be less. They should take less time. So gamma 1 is approximately 1. Gamma 2 is the communication time. Okay. Now gamma 2 total communication time. So as I told you, there is a all-to-all communication. No? So everybody talking to everybody else. So we start before communication, we time it, and after communication is ended, we time it. And the difference is TCOM, and that goes as number of nodes. No? So remember, each processor has many cores, so we computed with nodes rather than with processors. So with more number of nodes, the communication time is higher. Okay, so this is T n to the power minus gamma 2. Okay, so this communication time. I mean, total time is sum of the two. So if you just sum them up, then you'll get a total time. Okay, and so the total time will be this formula, and we compute these 3 exponents: gamma 1, gamma 2, gamma 2. Okay, so this was done in Sahin. This is published in a paper JPDC, Journal for Parallel and Distributed Computing. Now let's look at computation. So we have 3 data sets: 768 cube, 1500 cube, and 3000 cube. Now computation, this is for computation, T comp inverse. So we plot inverse because then we get a straight line. Now, so this slope is 1 in log-log scale. Huh? So P is the number of processors, and the slope is order 1. I'll show you in a table, it's order 1. It's kind of flattening for large processors. Here you can see it's kind of flattening. Especially you can see that for 768 cube. This is because if you have large number of processors, data is too less, and then there should be enough number of work to be done. Otherwise, you just take coffee, So, uh, so students must be given enough number of work. I hope I'm not offending any student, but if you have more work, then you'll have. Otherwise, the time taken will be, there'll be a lot of tea time here. Okay. Now we can. So this is for computation. Now communication with number of nodes, n is number of nodes. Here again, it kind of flattens. So this is because the data packet is also too tiny. So packet also, if you have one letter each, and you send it 1 letter each through a railway, it's not efficient. You should send a packet, a whole box of letters. So it's a good idea to send box of letters rather than 1 letter at a time. So here, if you have more nodes and only less data, 768 cube, then I'm not doing a good communication. So there should be enough data, okay, that these are showing up here. So in fact, it gets worse. You see, this is getting worse. But we take the slope in the linear regime, and the slope is around 0.7. And remember, that was the slope told by derived by two-thirds was derived by for P3D50 paper. This is the thing. Now this was strong scaling. No, so I'm doing it. For given processor, I vary the grid size. Okay. Now, so this for total time. So total time is okay, is linear, but the slope is around 0.7 because communication is dominant. I'm not, well, I can see the number here. This is first data point is around 10, T inverse, and here this is 100. So T inverse is 100, that means this is 0.01 units, seconds, and this is 0.1 second. So the 10 times. Communication for this data point is 10 times the computation. Well, there are, of course, you have to go down and you say, well, if you So communication is takes much longer time. Okay, that's what you see. So this is essentially T communication. Now we can compactify all the 3 plots into a single plot. How do I do it? So P by n cube multiplied by 768 cube. So here, what does it mean? If I have more data, then I have more processors. P by n cube, no? That is, if you give me more data, I will use more processors. Okay, so then this is like a packet size per processor or will be even, so increase the processors as well, number of. So this weak scaling, we discussed it in the past. Weak scaling is when processors and the data are increased proportionally. Okay, and is a nice compactification. This is called weak scaling. Okay, communication takes much longer than the computation. Now, these are the slopes. I don't want to get into all the numbers, but you can see that gamma 1 was computation, and this number is not very good, but 0.93 and 1.08. This number is around 1. Gamma 2, which is for communication, is 0.5 to 0.6. Okay, sometimes it's 0.7. So this is much less than 1. Okay, it's not linear. So that means if I have more processors or more nodes, then it gets worse. So beyond a while, FFT may be, you can already see the leveling off. Now, of course, this depends on the supercomputer we are using. It's a property of the switch as well as the processor. If it doesn't mean that the same thing will happen for other supercomputers. So the switch is different, but it's kind of is telling us that FFT is not very good beyond 2 lakh processors. Okay, people are trying it for a higher number of processors, but they've not gone much beyond 500,000 processors. Okay, now if a million processors, we don't know how will FFT scale. Well, basically it depends on the number of nodes. No? That's another point. If the number of nodes is not very large, then we will be getting reasonable scaling, because communication is essentially across nodes. Now total one is again around 0.7. Okay. Now the bottom number you should you would like to see. So efficiency, so we were asked to report efficiency. Now how do we compute efficiency? It is not time taken by a parallel processor divided by time taken by sequential processor multiplied by number of processors. Okay. Because these jobs cannot be run on a single processor. Impossible. Then what we did was we said, well, what is the best possible flop rating for each core? So each core has flop rating of 36 gigaflop. Okay. This is a Xeon processor, and that is, we can get it from the net. Okay. Now what we get, we can estimate how many operations are required per FFT. In fact, we know the number. For double precision is 5n log n. This is reported by FFT document. Okay. FFTW we are using at the backbone, and is 5n log n. So we know how much it does it take. So this is the flop rating we get in gigaflops for 768 cube. And so instead of 36, I'm getting 0.45. You see? So how much am I getting? If I get 36, 0.36 is 1%, right? 1 by 100 is 0.36. So I'm just getting above 1%. So we are basically getting 1.3% for 768 cube. Okay. Of course, nobody can expect to get 36 gigaflop. Okay. That's even if I run a single core, you can try it yourself. You turn off all other processors in supercomputer. In fact, you can run it on Param Sanganak. Run a job of just matrix multiplication on a single core. The total performance will never be 36 gigaflop. With the cache miss and so on. Probably we'll get something like 10 maybe if you're really optimizing it. Okay. In any case, so but we should try to get as good as possible. Okay, that's the maximum flop rating. So we get around, best is 1.8% for big grid. So 2% is what we get in this after all our trial optimization. It's not the best optimization, but that's what we got. Well, we can't claim to be the best. I mean, there are places we can still optimize. Now, one more run we did on a older machine. This was done. In fact, at one point, Sine had both the platforms, BlueGene as well as Cray. So that was Cray XC40. What I described in the previous run was Cray XC40. Okay, and we used all the nodes. Okay, whatever was available, we used it. So this is called use the whole machine. Okay, normally nobody uses the whole machine. In fact, we're not allowed to use the whole machine. What will other users do? But to test your code, you should use the whole machine. Exascale machine, that's what is a dream of application scientist. Can I run my code on the whole machine? Of course, not always, only for testing. Okay, and then we ran on the whole machine. Now we did the same operation on BlueGene P, which is an older machine. Now this is no more available. This has been discarded. This older machine, much less powerful than this. But look at the numbers. I don't want to bore you with the numbers, but here the slopes. Okay, these are the slopes. This for computation. We didn't. This gamma 1, gamma 2, and gamma. So gamma 1 is 1, gamma 2 is 0.7, and total is 0.881. Why? Because computation and communication were somewhat close. So this communication switch was very good. Okay, I mean this was a Torus architecture, T3, but computation, the processes were slow. Okay, this was 7 megahertz processors. Power PC, not very fast processor. So communication was good and computation was relatively slow. As a whole, we are getting very good efficiency for the, well, we are getting good exponent for the total. And look at the number of efficiency. Okay, so efficiency is here. For we are getting 11%. Okay, so you see the number 8%, 11%. So older machine gave a better efficiency for A50. Now I hope my statement is clear. You were getting 11% on older platform. Why? Because processors were weak relatively, but more importantly, the switch was fast. So in parallel computing, this is a key which not many people talked about. The referees were a bit, well, I mean, we try to highlight this in our paper, that it's not only the processor, it should be fast. We want the switch as well as the memory to be fast. Okay, and right now this is the bottleneck. Okay, so this is definitely a bottleneck for many applications, especially A50. A50 requires a fast switch, and they're not as fast. So processor getting faster data, more rapid rate, and switch also getting faster, but not as much rapid rate. Okay, so that's important observation. So I said BlueGene is around 10% efficiency, and Cray is only 1.5 or 1.8%. So our library is as good. I mean, you can see the numbers like 4096 cube, P3D took 8.06 and we took 8.18. Okay, sometimes we win. I mean, this is a lower time. This time must be lower, no? So this will win. Here they are winning. Okay, and okay, so this is the status of this software. Earth simulator, I just want to say, I mean, I'm kind of losing time. So Earth simulator is highly parallel vector supercomputer. Okay, now I'll tell you why highly parallel vector supercomputer. Now this is 2003. This even before BlueGene P. BlueGene P was 2007. We ran on 2007. Now 2003, I think Earth simulator was discarded in 2005 or so. Now look at it, top 500. Huh? This was the best machine for 3 years. This was the best machine from 2002 to 2004. Well, 2 years. Okay. Now this is a paper which is interesting read. This paper is interesting paper. Now efficiency is 57%, 56.9, or 55%. Okay, I mean these are two different numbers they quoted. So compared to 1.8% we got for Cray, this is huge. And why did they get this efficiency? On Earth simulator. But Earth simulator was used, I mean, it was designed for A50. Okay? It was designed for A50. Okay, so you can see that the CFD code on Earth simulator. They were supposed to simulate Earth using spectral method. So naturally, but of course, Japanese design is marvelous. Huh? I mean, if they put their mind on it, they really come with a very good product. Okay, so this you can understand from whatever we studied so far. So these are processors, no? Processors. There are 7 processors, 8 processors, 0 to 7, 8 processors. And these are memory, shared memory among the processors. Okay, so this is a one processor, this one. There are how many processors? The 640 processor nodes. The 640 of them. They're connected with a one switch. And there's a crossbar switch. Remember we had crossbar switch. Crossbar switch will talk to anybody in single hop. Please recall, okay? That's why I'm not giving any quiz or any homework, but these are general stuff. Crossbar was great, where any processor can talk to any processor, okay? So this is a any to any. That means in a single hop, I can reach anybody, okay? And that is why this machine is great for fast Fourier transform. Okay, and so I mean these are some more details how they're communicating, but let's ignore it. So this is within a processor. This is a processor, and so speed up is okay. Anyway, so this is what we have the story about A50. I mean there are some more papers, but this is the basic uh, bottleneck. Okay. So there are some more ideas that to communicate, communication and competition overlap. While things are being computed, communication can take place. But communication is so huge right now that overlapping is not going to help. Okay, this is only 1% of the task, 99%. So even if I overlap it, I'm going to get only 98%. Okay, so we need very novel idea, but we'll show you, and I have one slide. With the GPU, we can do better. In fact, GPU is giving a hope that we can really improve this performance. So RDMA is one more point. So RDMA we discussed now. So this communication can be enhanced by RDMA, which we did not do for A50K, but that's something one can try. So it's possible to enable RDMA in program itself. So you avoid copying, memory copy. So GPU based A50. So this is a new paper which we are going to submit it this weekend, hopefully. So scalable multi-node A50 on GPUs. This is on NVIDIA GPUs, and this is done by Manthan, Somdeep, and NVIDIA the scientists. Okay, and some students who were in the class last year. Okay, so there are 3 students of the same class last year. Okay, so these are the performance. Now you have to see number of process. This is a GPU, number of GPUs. P is number of GPUs. So we go from 8 GPUs to 512 GPUs. I'm going to work with GPUs a bit later. Okay, so we not told you how to work with GPUs, but we'll come to that a bit later. So this communication inverse and this competition inverse, similar plots, and this is slope 1. I mean this is basically slope 1. And communication again is a problem. So this is across nodes. Huh? So each node has 8 GPUs. So we are basically 1 node, 2 node, 4 nodes, 8 nodes, like that. We're going. And different grid. So this 4000 cube is this one. Okay. This is strong. So here, anyway, these are nice that we get linear lines in a log plot. So there is a scaling. In fact, if you put more GPUs, this still is expected to be linear. So in principle, you can use more GPUs. This is tapering out. This is basically, these are tapering down. So for this grid, which is 2000 cube, we should not use more grid points. Okay, that's not good. But 4000 cube, I can still use more GPUs. Okay, so for a given grid, there's a maximum number of GPUs one can use. Okay, if you go use more GPUs, then it's bad. You'll get bad performance. Now this picture is this table and pictures are kind of useful. So this efficiency, okay, the one I was telling you, this, well, it's not quite efficiency, but communication by computation. This is the ratio. Well, no, sorry, communication time by total time. So communication by total. So if I 8 GPUs, then we are getting something like 50% communication, 50% computation. Okay, it's great, no? I mean, we are able to use it reasonably optimally. So communication and computation are roughly equal with 8 GPUs. With 16 GPUs, 75% is communication, 25% is communication. So 3 times communication, 1 time computation. When you go to, well, of course, when you go to 256, then you're not doing well. This is basically 98% communication, 2% computation for this grid. But if I go to 4000 cube, then I am able to achieve 85%. So 85% communication, 15% computation. Okay, which is good. I mean, with 8 GP, with this many nodes, we get that. It's not great, but it's good. I mean, we hope we can improve it in future, but that's the status. Okay. Now, so with GPUs, there is a hope that we can improve this FFT. And so there's one more thing I wanted to discuss: hybrid FFT. So there's a lightning going on. So hopefully the power won't go away. Okay. So if it goes away, so then we'll close the class. So a hybrid FFT is combining OpenMP and MPI. Okay. So within a node, we do OpenMP, shared memory, but across nodes, one does MPI. And this is by Minini et al. They went up to 20,000 cores. Okay. And they're doing threading. Okay. Now this I will show you a bit later, but we will not do FFT. We are not going to use this code. But this for completeness. I mean, what are attempts being made to parallelize FFT? I thought I will also work with spectral method, but I won't start now. But FFT is a good thing to know. I mean, what are the complexities? This algorithm, I mean, the algorithm is simple, but it involves a competition between communication and computation, and it illustrates the problems in supercomputers. I mean, what do you encounter? Okay, so let me make some general remarks. So compared to finite difference, which one has more communication, finite difference or FFT? Now, please write FD as just write FD or an FFT. So please, everybody should type FD more communication or FFT more communication. So either write FD or FFT. 3 characters. Okay. All right. Looks like good. So I think I communicated at least that much. So FFT is much more communication. And FD was for slab. It is only with neighbors. So slab will have left neighbor and right neighbor. Okay. So you expect that finite difference, we can scale it to more number of processors. If you have 1 million processors, then finite difference code should still scale. That means I should be getting improvement in performance from, if I go from 100,000 to 200,000 to 400,000 to 800,000, I should be getting improvement all the time. Improvement means the time will be less and less. But finite FFT is not clear. If I go from, let's say, 200,000 to 400,000, time required, the wall clock, the total time required may be worse. So some job may take 2 hours, but if I use 400,000 processors, it may take 3 hours. But with finite difference, if you do it properly, then it will take less than 2 hours. Okay, when I increase the number of processors. So this is called scaling. Your code must scale. You should not, well, of course, at some point it will stop scaling, but that's where you say, well, I should not use for given grid processors more than this. And that's the reason all of you, if you are using HPC, I'm sure some of you are using HPC, please do the scaling. There was a question by Devaditya, I think. How many processors do I use? So you see, I have the data now. So for GPU, we saw that 2000 cube was not scaling beyond 128 GPUs. Then any run with 2000 cube, I should not use more than 128 GPUs. Okay, for that particular hardware. So once I have done the scaling, then I know how many GPUs I can use for a given grid. Is it fine? I mean, so please, all of you, I recommend that you scale your code. So some of you are using chemistry codes, fluid codes. You just run it, no, for and these are short runs. So by the way, don't do one loop. You should run it for something like 1,000 loops, assuming that each loop takes short time. Okay, 1,000 loops. So there's averaging over the loops, and 1,000 loops with let's say single node, which will be in a Param Sanganak. It is so you can do for 24 cores single processor, then 48 cores, then 48 into 2 nodes. Use all of it. Then do it for 4 nodes. Normally we do for double it all the time. Okay, don't do for 3, 2. I mean, that will be more data points, but you don't want to do too many runs. So we need to do 24, 48, 96, then 96 into 2 is 192, and just make a plot and see whether time taken is improving. That means it's taking less and less time. And please plot log scale, T inverse in the y-axis, and processor in the x-axis. Okay. Many of the codes, which is commercial codes or not commercial codes, but written by, I mean, you're using it as a package, then you will not be able to differentiate communication time and computation time. But then at least measure the total time. Okay. If you written your own, written on your own, then you can separate the communication and computation and do that. Okay. And then you should take a decision, how many processors should I use for a given grid or given complexity. I mean, if I'm using number of molecules will be a parameter for you if you're doing a chemistry thing. Okay. So that is a must, and that is what when you submit a proposal, in fact, IIT Kanpur, I wanted this to be done. Every group should submit this plot. Only then you get an account for that particular project. And this is the standard thing to be done by all across the world. That what application you want to run, and then you just say, well, I want to run it for this many particles or this many grid points. Then you say, well, how many do you need? So you have to make a plot saying for 5 iteration or 100 iterations, I took this much time. I'm going to run it for 1,000,000 iterations. So I need this much computer time. But you need to show the time taken for 100 iterations. Okay. And then only they will say, this code is doing okay, and we'll give them computer time. Now, this is, well, I mean, of course, it turns out this coding is not easy, of course. I mean, especially if you've not done it in the past. So the decision makers must be proficient in it. No? That's why they say, well, fine, let's give an account. So account is given, and then people don't run it efficiently. I mean, just imagine that you're given aeroplane, but you're riding on GT road.